There's a planet in our own solar system that we've essentially been misreading for 200 years, and when the James Webb Space Telescope finally turned its mirrors toward Uranus, the image that came back didn't just surprise astronomers. It quietly demolished a version of that planet that had been accepted since the 1980s. This is the part that gets to me. We have spacecraft that have visited Uranus. We have decades of ground-based observation. We thought we had a reasonable picture of what it was. Then Webb looked, and the picture changed. Let's start with what the telescope actually showed. The first James Webb images of Uranus arrived in 2 rounds. The initial release came in 2023, and a deeper, more detailed follow-up came in 2024. Both sets were captured using Webb's near-infrared camera, which detects wavelengths of light that human eyes can't see, and that most previous telescopes struggled to separate cleanly. What appeared in those images was not the smooth, featureless blue-green ball that most people picture when they hear the name Uranus. The planet looks electric. It pulses with structure. In the 2023 image, Webb captured Uranus surrounded by 13 of its 27 known moons, multiple faint rings, and a blazing polar cap of ice and methane haze that glows white and bright in infrared light. By the time the 2024 image dropped, the resolution and exposure time had been extended. Webb was now capturing details no prior telescope had ever resolved from this distance. Now here's the thing you need to hold on to as this story builds. The picture we had of Uranus came almost entirely from one source. The Voyager 2 spacecraft flew past the planet in January of 1986. That flyby lasted a matter of hours. It produced most of the close-range data we've had for nearly 4 decades. And Voyager 2 happened to arrive during a particularly quiet period of Uranian activity, at a season when the planet's south pole was pointed almost directly at the sun. So we saw Uranus at an unusual moment, and we called it typical. That mistake is now being corrected, one Webb image at a time. The first thing that strikes researchers looking at the Webb images is the polar cap. In the Voyager images, Uranus looked almost completely uniform. There were minimal cloud features, minimal contrast, nothing that grabbed the eye. Webb shows something fundamentally different. There's a concentrated bright zone centered on the planet's north pole that wasn't clearly visible during the Voyager flyby because at that point the North Pole was tilted away from the spacecraft. This polar cap isn't just a visual curiosity. It's atmospherically meaningful. Scientists believe it forms because of the extreme tilt of Uranus's rotational axis. Uranus is tilted at nearly 98 degrees relative to its orbit around the Sun. That means one pole spends roughly 42 years in continuous sunlight, and then the other pole spends 42 years in continuous darkness. No other planet in the solar system does this. The polar cap Webb revealed is a region where ultraviolet radiation from the Sun, combined with the chemistry of the upper atmosphere, is producing a thickened haze of hydrocarbon particles. The boundary of this cap is sharp. The brightness differential between it and the surrounding atmosphere is stark in the Webb images. And the exact mechanism driving its boundaries is still an open research question. That's the part nobody expected, not the cap itself, but how well defined the edge is and why it holds that shape. The data is in. The explanation hasn't fully arrived. Now here's where things get more uncomfortable for what we thought we knew. Uranus is technically classified as an ice giant, a category it shares with Neptune. The term refers to the composition of the planet's interior, which is dominated not by hydrogen and helium in the way that Jupiter and Saturn are, but by a slushy, hot, dense mixture of water, methane, and ammonia ices. This interior generates heat. In most planets, that internally generated heat contributes to atmospheric dynamics. Jupiter, for instance, radiates roughly 1.5 times the heat it receives from the Sun. Even Neptune has a substantial internal heat source. Uranus, according to measurements made during and after the Voyager 2 flyby, radiates almost no detectable internal heat at all. It appears to release barely more energy than it receives from the Sun. This is strange. This is genuinely unexplained. And the Webb observations are starting to poke at the mystery from new angles. The atmospheric dynamics visible in the Webb images show cloud structures and storm activity that seem inconsistent with a completely dead interior. There's motion. There's vertical structure. There's something happening inside Uranus that generates enough atmospheric pressure and chemistry to produce visible features from nearly 3 billion kilometers away. Whether that's evidence of a suppressed internal heat source or a convective layer that stops heat from reaching the surface in the same way it does on other planets, scientists don't yet agree. Webb can't see the interior directly, but it can characterize the atmosphere in enough detail to constrain what the interior must be doing. That work is ongoing. Let's talk about the rings, because the Webb images turned that part of the story upside down, too. Uranus has a ring system. It was discovered in 1977, long before Voyager, when astronomers watched the planet pass in front of a distant star and noticed the starlight flickering on and off on both sides of the disk before the planet itself blocked it. That flickering was the rings. The rings were later confirmed and mapped in more detail by Voyager 2, which also spotted 2 previously unknown rings. In total, the planet has 13 known rings. In visible light, those rings are dark. Extraordinarily dark. The particles that make them up are among the darkest objects in the solar system, reflecting only a few % of the light that hits them. In most optical telescope images, the rings are nearly invisible unless you're specifically processing the image to bring them out. In Webb's near-infrared observations, the rings practically glow. The brightness of the rings in the Webb images surprised researchers. The innermost rings, which had been faint and difficult to characterize from Earth-based telescopes, even with modern adaptive optics, are now clearly resolved. The 2 outermost rings, called Zeta and Nu, are also visible. The Webb image is the first time the complete ring system has been captured at this level of clarity from any telescope that wasn't actually there. What does ring brightness in near-infrared tell you? Potentially quite a bit. The thermal emission from the rings, their temperature, and the way they scatter infrared light all carry information about particle size, composition, and density. Early analysis suggests the rings may contain a slightly different composition than the darkest assumptions from the Voyager era, though this is still being worked out. What's certain is that Webb has given ring scientists a data set that doesn't exist anywhere else for this planet. Here's the rehook you need to understand the scale of what's missing. The Uranus system has 27 known moons. 5 of them, Miranda, Ariel, Umbriel, Titania, and Oberon, are large enough to potentially be geologically interesting, possibly large enough to harbor subsurface oceans. We have almost no data on them at close range. The only spacecraft that ever passed near them was Voyager 2, in that single January day in 1986, traveling fast and capturing what it could. Webb's 2024 image captured 6 of Uranus's inner moons with enough clarity to pull photometric data from them. Photometry measures the brightness and color of an object across different wavelengths. From that, you can begin to make inferences about surface composition. These aren't detailed surface maps, but they're the best data most of these moons have seen in 4 decades. And they're already showing that some moons look different from what Voyager's brief data suggested. Miranda, in particular, is an object that deserves its own moment of attention. It's one of the strangest-looking moons in the solar system, based on what Voyager captured. Its surface has enormous canyons, cliffs that are some of the tallest in the solar system, and a chaotic mix of terrain types that don't obviously fit together. The leading explanation is that Miranda was shattered by a major impact long ago and then pulled back together by its own gravity, imperfectly, which is why it looks like several different worlds stitched into one. Webb doesn't resolve Miranda's surface directly, but as the telescope accumulates more observation time on the Uranian system, researchers will be looking for any thermal or spectral signatures that could shed light on what's happening beneath that bizarre surface. This matters beyond scientific curiosity. We are in a period of solar system exploration where the question of subsurface liquid water is being taken seriously everywhere it appears, not just on the moons of Jupiter and Saturn. If any of Uranus's large moons contain liquid water oceans beneath their icy crusts, that expands the list of places in our solar system where life could theoretically exist. Uranus's moons are less studied, less funded, and less photographed than the moons of Saturn and Jupiter. Webb is starting to change that simply by looking. There's also a compositional story unfolding in the atmosphere that Webb is uniquely positioned to tell. Previous telescopes, including the Hubble Space Telescope, could observe Uranus in visible and ultraviolet wavelengths and detect the methane that gives the planet its blue-green color. Methane absorbs red light. What's left over after absorption is the blue-green tones you see in the classic images. Webb's near-infrared range goes further. It can detect the signatures of other molecules, including hydrogen sulfide, which was confirmed in Uranus's atmosphere only in 2018 using ground-based telescopes. It can potentially probe the cloud layers more deeply to understand what they're made of and how they're structured vertically. The atmospheric chemistry of Uranus is messier and more layered than the classic images suggest. At the very top, there's a clear stratosphere. Below that, a layer of haze. Below that, clouds made of methane ice. Deeper still, clouds of hydrogen sulfide and ammonia. And deeper than any telescope can reach, that slush of hot, pressurized ice that makes up the bulk of the planet. Webb is giving scientists a sharper view of the upper layers. Every improvement in that view constrains models of what must be happening below. This has implications for exoplanet science too, and this is a point researchers make explicitly. Planets the size of Uranus and Neptune, called ice giants, appear to be extremely common around other stars. In fact, they may be the most common type of planet in the galaxy. But our models of how ice giants form, evolve, and work are built almost entirely on Uranus and Neptune, the only two we can actually study up close. If our understanding of Uranus has been distorted by a single, unrepresentative flyby snapshot, then our models of ice giants everywhere are distorted too. Webb is correcting the sample. The 2024 images in particular were structured as a campaign rather than a single pointing. Webb returned to Uranus over multiple visits, building up observation time that lets researchers track atmospheric changes across weeks and months. Cloud features that appear in one visit and disappear in another tell you about atmospheric timescales. The polar cap's edge that looks slightly different between visits constrains how dynamic the upper atmosphere is. The rings, if they vary in brightness at all between sessions, could reveal information about how ring particles are distributed and replenished. This is what long baseline monitoring looks like, and it's something Webb is doing for Uranus that no previous observatory managed to sustain. There's an uncomfortable truth sitting behind all of this. The scientific community has known for years that Uranus is understudied relative to its scientific importance. Reports from planetary science decadal surveys, including the 2022 survey released by the United States National Academies, explicitly ranked a dedicated Uranus orbiter mission as the top priority for large-scale planetary science missions in the coming decade. That mission, if funded and developed on schedule, might reach Uranus sometime in the 2040s. That's not a typo, the 2040s. Until that spacecraft exists and arrives, Webb is the primary instrument advancing our understanding of the ice giants at any meaningful resolution. It's a space telescope designed primarily for cosmic and exoplanetary science, not solar system work, but it turns out to be extraordinarily capable at solar system targets because of the sensitivity of its instruments and the clarity of its infrared vision above Earth's atmosphere. The fact that it's doing this work is partly a tribute to the flexibility built into its observation program, and partly a recognition of just how empty the Uranus data archive truly is. When a general-purpose telescope is your best current option for studying one of the 8 planets in your own solar system, that's a civilizational statement about priorities. It's not said as an accusation, it's said as a plain reading of the record. What Webb is accumulating on Uranus is a new baseline. Every image, every spectrum, every photometric data point on those moons gets added to a foundation that the eventual orbiter mission will build on. When mission planners define the orbiter's science goals, they'll use Webb's observations to narrow down the questions. When engineers choose which instruments to fly, the atmospheric and ring composition data from Webb will inform those choices. This is how the telescope is functioning as a kind of advanced scout for a planet we've barely visited. And what it's scouting is a planet that turns out to be far more active, far more structured, and far stranger than the Voyager flyby suggested. That word, strange, is doing a lot of work. Uranus's axial tilt alone makes it unlike anything else we orbit around. The way it rolls on its side through the solar system, dragging its magnetic field at a wild angle, producing decades-long polar nights and polar summers, generating a magnetosphere so distorted and asymmetric it barely resembles the magnetic envelopes of other planets. The way it emits almost no heat from its interior, despite having one. The way its rings are made of the darkest particles in the known solar system, and yet glow in Webb's infrared light. None of these things are independently inexplicable. Each one has theoretical frameworks attached to it, but the combination, the full weight of how genuinely weird Uranus is when you look at it carefully, doesn't fully sink in until you see it the way Webb sees it. That image from 2024 is out there, and then you can find it. The planet sits against a pure black background, ringed in delicate infrared light, its polar cap blazing like a lit coal at the top of the disk. Its moons scattered in a rough plain around it, tiny and silent. It looks nothing like the pale blue marble of the Voyager era. It looks like a planet we're only now beginning to meet. Thanks for watching, and I'll see you in the next one.